Let's understand the one compartment open model with continuous IV infusion. It is an important concept in biopharmaceutics and pharmacokinetics. So let's get started. So in this method, a drug is slowly and continuously given into the bloodstream using an IV infusion at a constant rate. Why do we use IV infusion? So when rapid IV injection is not suitable, we use IV infusion, and to prevent toxicity and from high peak levels, and to maintain steady and controlled drug levels in the body. So the common drugs that are administered through IV infusion are antibiotics, theophylline, procainamide and all. So these drugs are given at a constant rate. Okay. And here we have the merits. So the advantages of IV infusion, continuous IV infusion is to facilitate, okay, or to it helps to control plasma levels, okay, plasma drug levels precisely in an individual, okay, and it is ideal for drug with narrow therapeutic range. The IV infusion, continuous IV infusion minimizes the fluctuations, okay, between the peak and trough plasma drug levels. So it provides an effective and constant plasma concentration of drugs in an individual. So the IV infusion allows the faster absorption and rapid distribution of drugs, meaning that it ensures or it provides the maximum bioavailability of drugs. It also helps to maintain the controlled blood levels. Okay, with the use of continuous IV infusion, we can administer medications, electrolytes, nutrients, and anesthetics in emergency conditions. So this route will be the ideal for unconscious patients who cannot take oral medications with, for example, IVD patients. So this IV infusion causes less discomfort to the patient by reducing the need for multiple punctures as we saw in the IV bolus. Now what happens after administration of drug? So the drug at a constant rate, that is zero order infusion rate, enters the body and distributes evenly in the whole body. Then it gets eliminated with the first order elimination rate constant Ke. So the rate of change in amount of drug in the body dx by dt equals to rate in minus rate out. Rate in is R naught minus rate out. Rate out is Ke. So when applying integration on both sides, we'll get this equation. If you want to know from how we got from this equation to this equation, I'll explain you in detail. As we know, dx by dt equals to rate in minus rate out. Now we want to integrate this equation to find the expression for x. X is the amount of drug at time t. So our equation becomes with the addition of x. After that, we are rearranging it. X terms will be on the left hand side and t terms will be on the right hand side. Okay, so this whole terms comes in the denominator, this goes on to the right hand side. Then we are applying integration on the both side. Then we are solving only this left hand side. Okay, so this left hand side, it is in the form of this formula, okay, this equation. So after applying this, it becomes in this form. Then our right hand side, it's just integration of 1 dt. So 1 dt becomes t plus c, integration rate constant. Then combining these two equations will give this. Okay, putting together will give this. To that equation, multiply with minus kx on both sides. So ke get cancelled out. Then we left out with this equation. This equation, when we convert it in exponential form, so it will be like this. In this equation, we are just finding out x. Okay, solve for x. We are just finding out x. So this terms goes there, so it will be like this. R naught goes here. Then when ke goes here, it is here in multiplication form. When it goes, it will be in denominator, in division form. So here we have to find a at time equals to 0 and x equals to 0. To this equation, wherever you find x or t, replace it with the 0. So our equation becomes this. So when we solve this after replacing 0, when we solve this, anything power 0 becomes 1. Okay. So we left out with r naught divided by k e equals to a divided by k. When multiplying with ke on both sides, we'll get r naught equals to a. When substituting this r naught equals to a or a equals to r naught, we'll get, we are substituting in this equation, in above equation. This is only. So in place of a, we can write r naught as we confirmed here. So our equation becomes this. When we factor out r naught divided by ke, our final equation will be the x equals to r naught divided by ke in bracket 1 minus e power minus ke t. Hope this is a clear concept for you. If you don't want to remember all this step, just remember that rate in minus rate out becomes this equation, our final equation. See, 2 pages took to solve to come to this equation. So just you can remember, after this equation you have to write this equation in the exam hall. It is beneficial for you only. To that equation we can replace x equals to vdc. Okay, as we know x equals to vdc, in place of x we can write vdc. So in place of x we are writing vdc and the whole term as it is. Then VD, we are sending it to the right hand side, so it goes in the denominator, so it becomes C equals to R naught divided by KEVD, then whole term. Then we, as we know, CLT, total clearance, equals to KEVD. So in place of KEVD we can write CLT. So in place of KEVD we are writing CLT. At start of constant rate infusion, at the start of infusion, the amount of drug in the body is 0. So no elimination will be there. As time passes, the amount of drug in the body rises gradually until a point where rate of elimination is equals to the rate of infusion. Rate in equals to rate out. So this point is known as steady state concentration or plateau or infusion equilibrium. So when you plot on a semilog graph, it yields a straight line with slope equals to minus ke divided by 2.303. This is our infusion rate or not. This is the infusion time. This is the CSS, steady state concentration. On the x-axis we are taking time, on the y-axis we are taking plasma drug concentration. After that we are finding it at steady state. So the at steady state, the rate of change of amount of drug in the body is 0, as rate in equals to rate out. So 0 equals to R naught minus KEX SS. R naught is the rate in minus rate out. So it, when you subtract this, it should be 0, equal to 0. So KEXS comes on left hand side. Then we are keeping XSS here only and we are sending KE, so it goes into the denominator. When transform the above equation in terms of concentration, we will get, as we know, x equals to VDC. So in place of x we can write VDC. So CSS VDC. CSSVD equals to R naught divided by KE. When we are sending the VD in the denominator on the right hand side goes in the denominator. And we know that KEVD equals to CLT. CLT equals to KEVD. So we wrote here. After that, our equation is the, on the above we have infusion rate, and in the below in the denominator we have the clearance. Now we have to substitute R naught divided by CLT equals to CSS in equation 3. Where is our equation 3? Here. Here in place of R naught divided by CLT we can write CSS. Okay, CSS we can write. So we are writing here C. In place of R naught divided by CLT we are writing CSS. So when multiplying this with this, it will become like this equation. When solving it out furthermore, we'll get this. Okay, this CSS e power minus KET goes on to the left hand side and C comes on to the right hand side here. Okay, after that we are keeping the e power minus KET here only, then we are sending it in the denominator. Okay, after we can write it as CSS minus C equals to CSS equals to divided by CSS equals to e power minus KET. We can write in this form also. When applying log, we'll get this equation. Log of CSS minus C divided by CSS equals to minus KET divided by 2.303. And when you plot a graph with slope KE minus KE divided by 2.303 and intercept log of CSS minus C divided by CSS, you will get this type of graph. So this IV continuous IV infusion helps us to keep plasma drug levels stable and to reach a steady state concentration where the IV infusion is equals to the elimination, and this IV infusion helps us to use when we need a precise control for drugs in emergency conditions. And thanks for watching this video. If you found this video, please like this video and share this video with your classmates and subscribe for more videos.